Now this section 4.3, it's on area under a curve, and then we'll hit 4.4 today as well. What we're trying to do is we're trying to find, if I have a function, let's call that f of x. If we have an interval, so a starting x value and an ending x value, we want to know what this area under here is. And the first way we're going to learn how to do that is we are going to approximate that area by drawing some rectangles. So I'm going to take this y value and make a rectangle because we know how to find area of rectangles. So we would draw however many we need to get all the way across. And if I can find the area of all these rectangles and add them up, it's not going to be the exact area under the curve, but it's going to be an approximation of that. So to find the area of one of these rectangles, one rectangle has an area of base. This base here, we're going to call that change in x, whatever we're changing x by. So we're going to do base times height, and the height is the y value. The y value in this case is going to be whatever the function is. So that would give me the area of one of these rectangles. If I want to add up all the rectangles, so I want to start with this rectangle and then I want to add this one and add this one, we are going to add them up. We add them up by using the summation notation. And we are going to start with the first x value and then go up to however many rectangles we have. So in this case, it would be 1, 2, 3, 4, 5, 6, 7. So it would be up to 7, but suppose it's not necessarily 7. N is the number of rectangles. So that's going to give us an approximation of that area. Now, the more and more rectangles we have, if instead of 7 rectangles, if I drew 20 rectangles in here, the area is going to be a better representation of the overall area. And if I had 100 rectangles, it would be even better, or 1,000 rectangles, or 1,000,000 rectangles. The exact area under the curve would be if I have an infinite number of rectangles. We can't have an infinite number of rectangles, so we're going to say that we want the number of rectangles to approach infinity. This gives you the area under a curve. So let's take a look at how this is going to work in a problem. So this one asks us to use the limit process, that's what we're doing, to find the area under the curve f of x equals 5 plus 2x, and the x-axis on the interval from 3 to 6. So the way we're always going to do that, at least the way we're going to do it by the limit process, so we're going to evaluate the limit as n approaches infinity of the sum I goes from 1 to n of the function. The function is 5 plus 2x, and I'm not going to use x there. We're going to talk about what we plug in for x, times delta x. And our delta x is, remember, the width of these rectangles, how big this is. So if I start at 3, this is 3, and this is 6, the width of each rectangle is going to be this distance, which is 3, from 3 to 6 is 3 units, divided by the number of rectangles I have. So in this case, delta x is 3 over, and remember we have n rectangles. And then for the x value, our x value, it starts at 3 and it goes up by delta x each time. So it starts at 3 and it goes up by delta x over and over again. So it goes up by 3 over n. We put the I in there because it's going to go up by 3 over n once, and then it's going to go up by 3 over n again, and then 3 over n a third time, and so on. once we get that set up, and we'll talk through that setup here again in a minute. Once we get it set up, we evaluate it the same way we did in the warm-up problem or the problems last time. I don't think we need to actually work through that. Sometimes on the test, she just has you set it up and you don't have to evaluate it. That would be it. All right, so again, these numbers come from, this will always be there. Limit as n approaches infinity, this will always be the same. Inside my brackets here, that is the f of x, the function. 5 plus 2, 5 plus 2x, so 5 plus 2x. Our x value starts at 3, so that's why this 3 is right there, and then goes up by delta x over and over again. So 3 plus the 3 over n, which occurs right here and right here, that comes from the distance. So in this case, from 3 to 6. From 3 to 6 is 3 units over n. It's always going to be whatever this difference is divided by n. Let's take a look at another one. Very similar problem, just a different function. So it wants us to use the limit process to find the area of the region between the graph of the function g of x equals 11 minus 3x and the x-axis on the interval from 1 to 3. So on these, we always have limit as n goes to infinity of the sum. I starts at 1 and goes to n. And then it's f of x times delta x. Our f of x is 11 minus 3x. Our delta x is the width of our interval from 1 to 3 is 2 units divided by n. That goes on the outside. And then our x value, what we plug in for x, starts at 1 and goes up by delta x over and over again. That's going to say 2I over n. I'm squeezing it in there. So that would be the setup. Again, you could find that actual area by distributing the 3, combine like terms, distribute 2 over n, and use your summation rules to find what that area is. We're just going to do the setup right now. Thankfully, there is a shortcut for finding the area under the curve, and this is section 4.4, which is probably the more important of the things we're doing today. 4.4 is on the fundamental theorem of calculus. There are 2 fundamental theorems of calculus. You're only going to learn one. You're going to learn the first one. First fundamental theorem of calculus. It says, let capital F of x be the antiderivative. Antiderivative is the same thing as integral of little f of x. And we can evaluate the integral from a to b of little f of x dx, which this is going to give you the area under a curve. By first finding the integral, getting the integral would be a capital F, and then taking f of b, so plugging in the top value, plugging in the bottom value, and subtract. So let's try one. This one asks us to evaluate the integral from 1 to 3. You always read that from the bottom up. So the integral from 1 to 3 of 3x squared dx. This is going to give us the area under the curve 3x squared from 1 to 3. So the first thing we need is we need the antiderivative. We need the integral of 3x squared dx. So if I integrate that, we add 1 to the exponent, and we divide by that. So I've got 3, and then I'm dividing by 3 plus c. So the integral is x cubed plus c. We have already integrated. We need to evaluate this from 1 to 3. We show that with the vertical line over here on the right side. And then it said f of b, b's the top value, minus f of a. So we're going to plug the top value in first. So if I plug in 3, I get 27 plus c. And then f of a, I'm going to plug in the bottom value, which is 1 plus c. And then it says to subtract those things. Notice in this case, I get, if I distribute, I get plus c minus 1 minus c. This plus c and minus c is going to cancel out, and that is always going to be the case. You actually won't need to put the plus c on there if it's a definite integral, if you have these bounds on there. This doesn't change what we did before. If those bounds aren't there, you need x cubed plus c as your integral, and that's your answer. But that plus c is going to cancel out. Notice the area under the curve is 26. Example 4 asks for the integral from 1 to 16 of root x dx. I'm going to change root x so that we can use the power rule. Root x is the same thing as x to the 1/2. Integrate, add 1 to the exponent. Divide by 3/2, which is the same as multiplying by 2/3. Plug in 16. 16 to the 3/2. You could evaluate on your calculator. Or split it up like that. It gives you 4 to the 3rd. So 64. Don't need the plus c. Plug in 1. Gives me 2/3. And subtract. 2 times 64 is 128. Gives me 126 over 3, which is 42. Example 5. What's the integral from 0 to pi of sine x dx? Integrate. Integral of sine x is negative cosine x. Plug in pi. Plug in 0. And subtract. Cosine of pi is -1. So I have negative -1. Minus, minus, I'm going to change that to plus. Cosine of 0 is 1. And 1 plus 1, I think, is 2. We're going to skip example 6. Example 6s. We're going to do this example 6, though. This one asks for the integral from -3 to 1 of the absolute value of x dx. Anytime you are integrating an absolute value functions are v's, which means they've all got straight lines. So the best way to evaluate the integral of an absolute value is to sketch a graph and then use geometry to get the area under the curve. So if I plug in -3, I get +3. If I plug in -2, I get +2. Plug in -1, +1. Plug in 0, gives me 0. And plug in 1, gives me 1. So the graph looks like this. We're trying to find the area under the curve, which is this area right here, as well as this area right here. And those are both triangles, so we can find the area under that curve by finding the area of the two triangles and adding them together. So area of a triangle is 1/2 base, which is 3 units, times height, which is 3 units. So that triangle has an area of 9/2. This little guy over here has a base of 1 and a height of 1. So I get an area of 5. So if you have the integral of an absolute value, we want to sketch the graph and use geometry to get the area under the curve. The average value of a function's average value is given by this formula right here. So average value equals 1 over b minus a times the integral from a to b of f of x dx. So if it asks us to find the average value of 3x squared plus 5 on the interval from 1 to 3, so we're going to do 1 over b minus a, 3 minus 1, times the integral from a to b of the function. So we've got 1/2 the integral from 1 to 3 of 3x squared plus 5. Integrate gives you x cubed plus 5x. Evaluated from 1 to 3. Plug in 3, gives me 27 plus 15. Plug in 1, gives me 1 plus 5. Subtract. 36, 1/2 of 36 is 18. And then the last thing is the mean value theorem for integrals. And all that says is the average value of a function is equal to its function value somewhere on the interval. So if we had that previous problem and it said, use the mean value theorem for integrals to find the value of c. So we would find the average value, we would do all this work right here, find the average value, we would get 18. And then we would take that 18 and we would set it equal to the function. 18 equals 3x squared plus 5, and solve for x. And that's all there is to it. Take the square root of both sides, square root of 13 over 3. Is 2.082, technically plus or minus 2.082, but we're guaranteed a number somewhere in between 1 and 3. So the only one of those between 1 and 3 is 2.082. Anyway, that is section 4.3 and 4.4.